Thank you for everybody for joining this session that I'm excited to chair. It's with great pleasure that I introduce Professor Dr. Gitta Kutyniok from Ludwig-Maximilian University in Munich. So she has a long history of contributions in research in harmonic analysis, frame theory, as Rich mentioned earlier, compressed sensing, image processing, and more recently, she's gotten an interest in deep learning. At present, she's the Bavarian AI Chair for Mathematical Foundations of Artificial Intelligence at the Institute of Mathematics at the Ludwig-Maximilian University of Munich. And she's held various positions at the Georgia Institute of Technology, at the University of Gießen, WashU St. Louis, and a lot of other interesting places. And she's going to be talking to us today about graph neural networks and generalization. Please join me in welcoming Professor Kutyniok. Looking forward to hearing your talk, Gitta.
Thank you very much, Demba, for the very nice introduction. And also thank you very much to the organizers for inviting me. So let me start sharing my screen. Okay, yeah, so I would like to also, I think, as some of the previous talks, focus on generalization, which is in some sense, I guess, the mystery, also why overparameterized systems generalize that well. And in this talk, I would like to focus on a particular class of neural networks, namely graph convolutional neural networks. But let me start in saying that I think we all know how tremendously successful deep learning and in particular general AI is for a variety of different applications in public life, but then also in sciences. So here are a couple of those which I think all of you know: self-driving cars, surveillance tasks, legal issues where job applications are pre-screened by neural networks, and also the whole healthcare sector, which right now, unfortunately, is much more important than it was before. But at the same time, I think we are also aware that there are not that many theoretical results which actually explain why these methods work that amazingly well. And now if we go in a bit more in the direction of sciences, then we also observe that there's another phenomenon, namely that neural networks and AI are used in combination with model-based methods, which makes then developing the theory even more challenging, but also even more exciting. So let me start and introduce a bit the notation I will use and delve a bit more into, let's say, the mathematics of deep neural networks and deep learning. And then in the second step, we will come then to graph convolutional networks. But I would like to first motivate what are the key theoretical directions I see in this area. And then we will come to the concrete topic of this talk. So what is a deep neural network? I think everybody already knows this and has seen this several times, but let me start fixing a bit the notation. So it's a highly structured function from RD to RNL, which looks like this. It's a concatenation of affine linear maps, so AX plus B. And then to bring in some nonlinearity, you have a nonlinear function, so-called activation function, which is univariate. And it's then applied component-wise and then followed by another affine linear map. Sometimes you have also pooling layers in between, but let's forget about those for a moment. And so here, this is a typical depiction of a neural network. Here you have input dimension 4, and these connections mimic in some sense, the affine linear map. And important criteria here are the number of layers. So deep neural networks, highly overparameterized neural networks are particularly effective these days. So that's why actually right now everybody's talking about them. Another important notion is also the number of neurons, so the total number of neurons if you sum over the map. So let me just very briefly go through this procedure, how you use neural networks, and then we will see how the theoretical directions, which to my mind needs to pursue, arise from that. So how do you use a neural network? Well, I mean, you have a complicated function in the background, which is defined maybe on some manifold. Maybe it's a classification function. And maybe usually, I mean, people like to separate cats from dogs. So let's say in one area you have cats, in the other area you have dogs. And maybe your function maps those to the value 1 and the other to the value 2. But only what you have at hand are sample values, so you have images with labels. And for that, you would like to recover and learn the function f. And the first thing you need to do, you need to decide which architecture to choose. This is already a non-trivial process. You need to decide how many layers to take, how many neurons in each layer, which activation function to take. Maybe you don't want a fully connected network, so you pre-select certain entries of these matrix to be equal to 0. Then once you have decided that, you need to learn the network function. So you need to learn the affine linear maps, the ingredients of those. And so this you usually do by stochastic gradient descent. So you aim that your network function in your images, in your samples, is close to your labels by a loss function, closeness given by a loss function. And maybe you would like to also impose certain restrictions on your affine linear maps, maybe sparsity. You want to have a sparsely connected neural network. So once you set off this optimization problem, then the typical way to solve it is by stochastic gradient descent, which gives you this network, and hopefully you're close to your function f, which you aim for. Now from this, the directions which one is interested in developing theory, and let's say the main directions, arise in a very natural way. The first is concerning the architecture. How powerful is a certain architecture? Can it represent the correct function? So that's expressivity. And to my mind, this is maybe the furthest developed direction concerning theory of deep neural networks, because that was already very heavily studied when there was, let's say, the first wave when shallow networks were considered. So this uses, for instance, tools like approximation theory. Then the learning procedure. Current learning algorithms, do they converge? What are the starting values? Can we get stable learning algorithms? Also methods like differential geometry, optimal control, like neural ODE optimization come into play there. And then generalization, which I think is maybe the biggest mystery, I mean, at least to me, for neural networks, because if we are in the highly overparameterized regime, neural networks generalized amazingly well. So they've only seen the test data set, but on the training data set, but on the test data set, they still perform in a quite similar way. So this typically requires or is approached by learning theory statistics. And so these three areas are exactly the three components. If you view a neural network as a statistical learning problem, the three components of the error of a statistical learning problem, namely approximation, the algorithm, the algorithmic error, and the sampling error. And then there are other directions which I think are also quite intriguing these days. For instance, interpretability. You have a fixed neural network. You aim to understand how it reaches decisions, which in some sense you can also view as a circumvention of these other three directions. Since if we can understand them in really depth, maybe we don't need interpretability, but still we will always have neural networks which are already there, which we don't have any control of how they are trained, and then this is the way to go. But as I said in the beginning, this talk will be now about generalization aspects. And so one key observation in this whole area, and I think which is somehow the mystery, is that if you have highly overparameterized neural networks, so typically very deep neural networks, that they show a surprisingly small difference between the training and the testing. And so, I mean, you can think of different reasons. I mean, it could be, for instance, properties of the architecture, so that goes more in the direction of expressivity. Maybe it's more regularization techniques during training that would go more into optimization and learning. But in some sense, I mean, all of those don't really unravel the true mystery of the generalization ability. And so therefore, there's a lot of research and from different directions to approach this problem and aim to understand this ability, this amazing ability of neural networks. And so there's a very classical picture, which I think most of you have already seen, where here you have the capacity of the hypothesis class. So here, in a sense, the size of the neural network, the error, you have the test error and the training error, and this is, let's say, the viewpoint from classical statistical learning theory, where at some point the training error goes down, but then the test error goes up, and so this is this overfitting. Now, this mystery, which one also aims to solve, is that if we are in the situation of neural networks, that at some point this curve again goes down. So if you're really in the highly authorized regime, then the test risk again goes down. And so this is why, the main reason also why neural networks are that popular these days. And I mean, there are a lot of approaches to tackle this problem. So classical approaches, for instance, like the VC dimension, Rademacher complexity, uniform stability, and also very new methods like the neural tangent kernel. And there's a long list of papers, much more than I have here, which accelerates now, I mean, the last years to understand this phenomenon. And in this talk, I would like to now focus on graph convolutional neural networks and analyze their generalization ability. Okay, so let me start by introducing my collaborators. Ron Levy is a brilliant postdoc in my group. He did a significant amount of the work which I would like to tell you about. There are two master students, Wei Wang and Lorenzo Bucci from Italy, and last but not least, Michael Bronstein, whom I think you all know from Imperial College in London. Okay, so what are graph convolutional networks? I mean, you can see them in some sense as a generalization of classical convolutional neural networks in Euclidean domain, because you can view Euclidean domain also in some sense as a graph. And graph signals in this setting are functions which are defined on the graph nodes to some RC. And so how is the graph convolutional neural network structured? We will see that in a bit more detail in a moment. Well, I mean, you have your graph signal, you apply convolution to it, like for a normal convolutional neural network. Then you use an activation function, then you do pooling, which I already mentioned before, and then you keep going. Why are graph convolutional networks that popular? Why is it interesting actually to consider them? Well, because I mean, there are numerous applications where they are crucial. So one is, for instance, recommender systems, where companies would like to recommend certain products to customers. A second is social networks, for instance, fake news detection in such social networks, but also other questions which you can ask in this setting, how news are spread and so on. And then certainly also in science, like chemistry, you see, I mean, the molecule has a structure of a graph, so graph convolutional networks you can use for maybe analyzing properties of molecules to a certain extent. Good, so these are graph convolutional networks, and now we want to ask the question, how do they generalize? And what is intriguing here is that in this setting, there is a certain aspect of generalization which does not appear for normal convolutional neural networks. And this is an aspect we would like to now analyze. So graph convolutional networks get, well, I mean, graphs as input, that we just said, but there's something, a special phenomena which appears. So let's take a look at these two graphs. You see, I mean, they look different, but in some sense, they also look similar. It seems that they mimic the same phenomena in a sense. But they might be even sampling from the same continuous phenomenon. And so now let's assume your graph convolutional network gets as in its training set only this graph. So then certainly we hope, if both graphs mimic the same phenomena, that the neural network is able to generalize to also graphs of this type. Yeah. So the question is, if I have graphs which mimic the same phenomenon, is a convolutional neural network a graph convolutional network then able to generalize to others of the same type? So, or here, I mean, this is called the concept of transferability. If two graphs mimic the same or model the same phenomena, does it then happen that the graph convolutional network has the same or approximately the same repercussion on both graphs? Yeah, so you see that that's one aspect of generalization ability, which does not happen in the Euclidean case. And what I'd like to show you in this talk is that this is true. So for graph convolutional networks with spectral filters, transferability can be rigorously proven, and we can get very precise error bounds on this. Good, so let's walk a bit through how a graph convolutional network is structured. As I already said, I mean, there are activation functions, which is quite easy because it's applied component-wise. Pooling is also easy to explain. It's done by graph coarsening, which you see here. And the big question is, how do you define convolutions? There are two main approaches. One approach is the spatial approach, where you have your filters like a window, you slide them on the graph, and each time you aggregate the features from the neighboring graph to this, from the neighboring nodes to the nodes you're currently considering. The second approach is a spectral approach. So there you do everything in frequency domain. You use the convolutional theorem, and the filter you then apply in frequency domain as a multiplication. And so there was a common belief for a long time that spectral graph convolutional networks do not exhibit this transferability property, which I just told you about. And we will see that this is not true, so we can debunk this misconception. And we will then also see numerical results that actually spectral graph convolutional networks are at least as good as the state of the art of spatial approaches. Okay, so let's introduce a bit spectral filtering. So I think this, I presume everybody knows. I look at undirected weighted graphs. So I have vertices, I have edges. I have the notion of an adjacency matrix in which I collect to which extent these the nodes are connected. And then I also have the degree matrix by, for each node, adding the edges which are assigned to this one node. And then there's a notion what's called a graph Laplacian. So if my D is the degree matrix and W the adjacency matrix, then I can define an unnormalized graph Laplacian in this way, just by the difference of the degree matrix and the adjacency matrix. And then I also have what's called a normalized graph Laplacian by, well, normalizing it. Good, and so in the following, we will always use this notation and not, in that sense, distinguish between the unnormalized and normalized one, but it will be the normalized graph Laplacian. So what is this graph Laplacian? It is an operator, it is self-adjoint, and it has eigenvalues and eigenvectors. The eigenvalues are related to frequencies, the eigenvectors to Fourier modes. So in some sense, one can say that a graph Laplacian, in some sense, senses the geometry of the graph, and you see several graph Laplacian eigenvectors of this sort of dump shell type graph. You can see how the frequencies actually change, first in this connection, but then also inside of these blocks. But you see, I mean, I hope that this is very much adapted to the geometry of the graph. Okay, well, so this is a graph Laplacian, and certainly it generalizes the normal Laplacian from the Euclidean setting. So here I said the eigenvalues are connected to frequency, the eigenvectors to Fourier modes. So if we look at the normal Laplacian setting in the Euclidean domain, then I also have the eigenvalues of frequency and the eigenvectors or these exponentials, the Fourier modes. Okay, good. So this is a graph Laplacian. Now the question is, how do you define spectral filtering. There's a very canonical way to do that. I take the graph Laplacian, I compute the eigenvectors of it, and then I define the convolution operator, the convolution, in this way. These CJs are the filter coefficients. And you see here, I have the eigenvectors and also here. So the action of the convolution operator on an f, so a function on my graph, is defined in this way. And so this is the normal way to define convolution, where, as I said, these are the filter coefficients. This is canonical, but it also bears a problem. Actually, two problems. First of all, it is computationally extremely demanding. Now imagine you have these social network graphs. I mean, they are huge. And computing the eigendecomposition is a tremendous task, and it's often even not possible. Yeah, so you can basically forget about having the eigenvectors of the graph Laplacian in that case. Even worse, I mean, you also don't have, generally not an FFT for graphs, which you would need for computing this in a fast way. Okay, so that's already bad. But I mean, even worse, if you do it that way, this is not transferable. Why? Well, now imagine, I mean, I have one graph, and now I perturb it slightly. Then the eigenvectors could change significantly. And so since here I have something constant, that means that this operator, if I just perturb the graph slightly, now does, I mean, the filter does something completely different. Yeah, so in that sense, the eigendecomposition is not stable to graph perturbations, and so this filtering process is not robust to perturbations. Yeah? Okay, so that's not the way to go. But there is a way to actually introduce spectral filtering in a more smart way, so that you can actually cope with all those problems. So let me explain to you how this can be done. I mean, it's using a technique, what's called functional calculus, which, I mean, some of you might have already heard about. It comes from the area of functional analysis. But let me walk through this with you and show you what one can do. So what is functional calculus about at all? I mean, it's the following concept. You have an operator, like here you have this self-adjoint operator, where you have decomposition like this, where these are the eigenvectors and these are the eigenvalues. So you have this decomposition, and now you can ask, okay, I have an operator. Can I apply a function to it and get another operator? So for instance, imagine this function is the square. Yeah, so then, I mean, you could think, well, I take the operator, I mean, squared. I mean, it seems to be a normal operation, which I can apply. But in general, there is a concept of this functional calculus where you can apply a function to an operator and get another operator. And then the formula, you see how it changes. I mean, then this G is applied here to the eigenvalues. Okay, so I think it becomes also quite, let's say, clear if we take another specific G, namely a rational function. So if my G is a rational function, then this operator can be explicitly computed. You see, I mean, you just plug in the T here and the T and the T here. And so this, you see, then is an operator. And this can be computed even without knowing the eigenvalues, the eigenvectors. Good. Okay, so the concept is I have an operator, a self-adjoint operator. I can apply a function to it. I get another operator. And it's very easy to do that if my G has a nice form, namely such a rational function. Good. Okay, so now I do the following. I define my filter in a slightly different way. My filter are now not these coefficients. My filter is now a function. Okay, so my filter is a function, and my operator instead of the C is this function applied to the graph Laplacian. And then I get a decomposition like this. Yeah, so again, the difference is here I have filter coefficients. Here my filter is a function which I apply to this graph Laplacian. Okay, so this seems awfully complicated. So what's the advantage now? Well, first of all, it solves this instability problem. Because, yeah, remember the problem we had? We had a graph, we have another graph, we perturb one. Then we said that the eigenvectors might change a lot. That certainly still remains true, but we have the following advantage. These might change, but the lambda j's will also change accordingly. And so that this change will counterbalance this change, which did not happen here because the CJs are constant. Yeah, so this gives this stability that I have here, these eigenvalues also in play. Okay, so this solves the instability problem. Also, the computational problem is solved if my G is a rational function, because then, let me go back. As we said before, if G is a rational function, then G, also think of here the graph Laplacian, I can compute directly. I don't need any eigendecomposition for that. So I don't need to compute the UJs and the lambda j's, I can compute this directly. Yeah, so therefore, using these functional calculus spectral filters, I solve both problems. Good, so this gives me a very nice way to define filters for a graph convolutional neural network. Okay, so now since we defined spectral filtering, let's head towards transferability. Yeah, remember this was the special generalization ability of graph convolutional neural networks. And what we now first need to do is we need to define what we actually mean precisely by graphs mimicking or modeling the same phenomenon. Yeah, so we need to make this precise, otherwise, I mean, we cannot develop a theory. Okay, so let's look at weighted graphs. I mean, a weighted graph has certain points, and the weights give us a correspondence between those points. Then we have another concept in mathematics, which are called metric spaces. So these are just points with distances. So it's just points in the room with distances. And now what we will do is we will think of graphs as a discretization of a metric space. So just think of you have something continuous overlying it, and your graph is like a sampling of it in a sense. Then, I mean, if your distance here in this metric space grows, the weights go down. Okay, so if I have two graphs, I mean, then they represent the same phenomena if they are discretizations of the same metric space. Yeah, so I have something continuous, and if the graphs are a discretization of the same continuous object, then they represent the same phenomenon. Okay, so how can we now compare repercussion of a filter? So I have these two graphs, and I have a function on the continuous structure which overlays both graphs of the metric space. Okay, so that's my f. So it's defined on this continuous object. Now I go down on both graphs, on this graph and on this graph. That's my sampling S1. Now I'm on the graph. Now I can apply my different filters. So it's the same filter, but adjusted to the different graphs. So I apply here my filter. It's the filter G applied to the graph Laplacian. Remember, this was our filtering procedure. And here I apply the same filter G, but here now certainly to the other graph Laplacian. And now I go back to the continuous setting. So I recover or interpolate. And now in this continuous setting, I can compare. So now I can compare these repercussions, and then I hope that this is approximately equal to 0. So I have this continuous world, I can go down, there I have my filtering procedure, and I can go up, and then I can compare. Okay, good. So we need a couple of notations. We have our analog domain, here, well, Borel space, Laplacian, we have our digital domain, the graphs with the graph Laplacian. We have what's called Parley-Wiener spaces, so these are band-limited spaces on the analog domain. And then we have a sampling operator, which allows us from the band-limited space to go down on the graph, and we have an interpolation operator which maps it back. Yeah, so this is like a DSP framework, digital signal processing. Okay, so now let's take a look at the ingredients of our result and then also our error estimate. So what we first need to do is we want to compare transferability to the continuous setting. And then in the second step, we compare it with respect to two graphs. Okay, so we first look at this error, which you want to estimate. So let's look at the ingredients. We have our signal. We bring it down on the graph. We filter it. F is my filter, and we bring it back up. And we compare it to if I just leave it in the continuous setting and filter it there. Yeah, and then later on we have another graph. But this is the first error we want to estimate. And what comes into play in the estimate are two terms. One is the transferability error of the Laplacian. Yeah, so you see it's basically the same, only that F is now the identity. Okay, so my filter is now the identity. So this is the transferability of the Laplacian. And the second is what we call the consistency error. So this is how close the sampling and reconstruction procedure is to the identity. So in some sense, how dense the sampling is of the graph. Okay, and so this is the first result we derived. So let's take a look here first. This is the transferability error of the filter. It's exactly what we saw before, only now that the filter is called G instead of F. I hope that's not a problem, but our other ingredients are the same. So you have here the Parley-Wiener space, then your sampling procedure, the filtering, the reconstruction, and you compare it to if you just stay in the continuous setting. And the error estimate consists of two components. Here you have the transferability of the Laplacian. It's written now a bit different from before, but you can write instead of this F, S also the R here. The second ingredient is the consistency error, which again you see is exactly from the previous slide. I check, or this error depends on how close this is to the identity SR. And then you have other ingredients. So you have here, you see, the reconstruction error bound for that operator. You have the Lipschitz constant of your filter involved, and you have also another norm associated to your filter involved. You can also apply everything to a specific function of your Parley-Wiener space, then the error estimate looks like this. But the main message here is that you get this estimate. Transferability of the filter can be estimated by the transferability of the Laplacian plus the consistency error. And in fact, this result, which I just showed you, holds in much more generality. So again, this is copied from the previous slide, the estimate which we have. And you see the setting which we considered is this setting. So my M is this Borel space, G is a sampled graph, and then I have sampling and interpolation. But it also applies, for instance, to this setting, where I have a very fine graph. My G is a coarsened graph, and then the S and the R are coarsening, which you see here, and piecewise interpolation to map it back to the fine graph. Or my M could be also a graph, just a normal graph, and G could be a perturbed graph. And then S and R are just the identity. Yeah, so there are various settings you can consider this result in.
Gitta, my apologies for interrupting. There's a quick clarification question.
Okay, sure.
The question asks, what kind of assumption on the graphs are we making by the band-limited assumption in the analog domain?
So on the graph, you have as an input for, so you mean where S maps to?
Yes.
So first of all, I mean, there are no general assumptions, just in any graph. So you just have a normal, I mean, it doesn't, yeah, just a normal graph. I mean, there are no assumptions per se. I mean, certainly then assumptions come into play in this result in a lot of ways, because I mean, so the S certainly depends on that. I mean, if you, let's say, if a continuous domain and your graph just consists of one point, I mean, then this error will be huge in a sense. And also this, I mean, this will change very much on the sampling procedure. So if, for instance, you have some continuous domain and you sample your graph in a very unequal way, then this will also become large. So in that sense, I mean, per se, I mean, you don't have any specific assumption on the graph, but it comes in to play implicitly by this estimate.
Thank you.
Sure. Okay, so now, I mean, as I said, I mean, this was the first result, but this is the result which now solves this transferability problem. You see, I now have two graphs with two graph Laplacians associated to this. I have my, let's say, continuous space where I have a Laplacian. I have my graph convolutional network, which is a ReLU graph convolutional network with Lipschitz filters. And then I have the graphs in the different layers. And these two assumptions you see come from the previous result. This is an error estimate on the, or a condition, I should say, hypothesis on the transferability error of the Laplacian. This is a constraint, or a hypothesis on the consistency error. So these two deltas in some sense bound what we had before as ingredients. And so now, I mean, this error which you compute is the error where you have now your function on the continuous setting, you pass it through, you map it, let's say, on the first graph, and you pass it through the neural network. And then this is the overall transferability error of the entire graph convolutional networks. You see, the number of layers here also comes into play, where you pass things through. You see the delta from these estimates come into play. You see the D come into play. So let me remind you, the D was the Lipschitz constant of the filters, and you see also the dimension of the Paley-Wiener space comes into play. So this is the error estimate which you have for this transferability now, for the transferability ability of graph convolutional networks. Okay, you can now ask the question, okay, so the consistency error, I think I can understand control. So it depends on, if you view it as a sampling procedure, how dense the sampling is, to how close this reconstruction, sampling and reconstruction procedure is to the identity. But what about the transferability error of the Laplacian? And so the question is it reasonable to assume that that's actually small? And we have one result, and it's just an informal statement of that, which basically says that if the graphs are random sampling points from the continuous domain, then you have, I mean, this transferability property happens with high probability. So then the graph Laplacian approximates the continuous Laplacian with high probability. So then, in that sense, for this situation, you can control also the transferability of the Laplacian. Good, so let me now come to numerical results. And for this, we first need to, let's say, analyze in which way graph convolutional networks manage transferability, because there are different ways. So there's what one calls concept-based transferability and principal transferability. So the concept-based transferability is you have already training set where you already have different types of graphs. which model the same phenomenon. I mean, then the network certainly learns in some sense, hopefully, how this transferability works. And if then there is another graph which models the same phenomena, is able to transfer. The other is the principal transferability, which is some sense the built-in capability of graph convolutional networks, which we just studied, to transfer. So this is the situation where you maybe only in the extreme case have one realization of this phenomenon, and then the neural network sees the other realizations or modeling of the phenomenon only in the test data set. And so the success of spectral graph convolutional networks somehow relies on both types of transferability. So what you see here is an experiment using images, and the neural network only saw images of one resolution, and the question was, can it generalize also to images of different resolutions? Yeah, so in that sense, you can imagine, I mean, you have a continuous image and a digital image you can always view as a, let's say, discretization of a continuous image. And so here, the KLINet is a spectral graph convolutional network using these functionalytic filters, and the other, the MONET, is a spatial graph convolutional network, and you see the spatial one does much better in this task. Then there are different experiments which you see here from some sites here, citations, where one can compare the Laplacian transferability to the filter transferability. We saw in our numerical experiments that we would expect somewhere like a linear relationship, and you see these experiments shows that, well, approximately somehow a linear relationship seems to be reasonable. I think it becomes much more evident if you look at the next experiments, where here you randomly remove edges. So this is in some sense the perturbation which you impose. You have here again the Laplacian error, the filter error. You see again you have this linear relationship between those two errors. You can randomly add edges as another, let's say, perturbation, or you can also randomly remove vertices. In all those, I mean, you have this relationship which also our theoretical results show. And what was very intriguing and interesting for us was that just very recently, also two colleagues did an extensive numerical study of spectral graph convolutional networks, namely those which come from these filters which I described to you, so from function analysis. And so they tested those in the single graph. They tested those in the multiple graph setting. So before, I mean, most numerical experiments only dealt with the single graph setting, but they now drove an extensive analysis in this with different tasks, with different rules. And what they showed was that this, what is a spectral graph convolutional network based on these functionalytic filters, reached the state of the art. And so there are many tables in this paper where you see that spectral graph convolutional networks, as you compare them to spatial ones, behave at least as good in these multiple graph settings. So in that sense, I mean, if there's a chance to use a spectral filter, then I mean, the recommendation would be to go for it. I should also say, I mean, I talked about graphs mimicking the same phenomenon. There are other ways how you can define that. I mean, also using the new graphone approach. We also have some very recent results in this direction. So there are various ways you can also deal with that and handle that for a theoretical study. But let me now conclude my talk. So we talked here about graph convolutional networks, which are a generalization of classical convolutional networks, classical Euclidean domain convolutional networks. And the question we studied here is, why do they have this amazing generalization ability? And in particular, how do they generalize to graphs which are not seen in the training data set, but which model the same phenomena. And so this is one aspect of generalization ability. It's called transferability. There was a belief that that's not true. And so I showed you here that this is actually true. We can rigorously prove this. We can make the definitions precise, and then we can get a very precise error estimate that the filter transferability. So this error is bounded by the Laplacian transferability and the consistency error. And we also saw numerical experiments which showed that these type of graph convolutional networks reach at least the state of the art. And with this, I'd like to conclude and thank you very much for your attention.
Thank you. Thank you for your talk. I want to encourage the audience to use the chat box to ask questions. And I thank you, Gitta, for finishing in time and actually with 3 minutes left. So if people are interested, I can monitor the participant and see if you want to unmute yourself and ask questions.
I think there's one question, Demba, in the Q&A box around the assumption on the graphs. Maybe Gitta, or you could read it because it's from an anonymous attendee.
I can read it.
Yeah.
Perhaps I can ask a clarification question following up on that, Gitta. I think the question, if I understood it, so if you assume that on the continuous space you have band limited functions, does that imply anything about the graph? Does that lead to any restrictions on the graph, or does that not have anything to do with the graph?
Not per se. I mean, so you can define. So let me go back. Yeah. So I mean, on the continuous setting, I mean, it's a metric space. So there, I mean, this is independent. The definition there of metric spaces. Let me go back to it. Yeah. So here, I mean, these band limited functions are independent on the graph, which is underlying it. So there, I mean, you just define it independently, and then, I mean, certainly it's a matter of the sampling operator. So to bring it down to the graph, but here, I mean, per se, you don't have any assumptions. I mean, it could be even, let's say, you have a graph just with 1 point. So.
Makes sense. There's a question from Jasper Tan. He thanks you for a very interesting talk. And then he asks that now that we have insights on transferability, do you have any thoughts on what other specific properties of graph CNNs are open questions that can provide insights on generalization? And I can repeat this if you want.
Yeah, I mean, that's an interesting question. Thank you for that question. So I think it's a question of, let's say, generalization ability for graph convolutional networks. I mean, certainly this is a specific aspect which you can model very precisely and then also solve. I mean, so concerning the generalization ability, I mean, since for normal classical convolutional networks, I mean, these questions are still, I mean, a lot of questions there are still unsolved. Yeah, it seems out of reach right now to solve the generalization, the overall generalization question for graph convolutional networks. Here, it was one aspect which actually did not appear in the other setting, but I mean, I wouldn't think of any, let's say, other, let's say, setting for which one would not need to solve the classical, I mean, the problem in the classical setting first. So in that sense, I think progress first needs to be done in the classical setting before then, I mean, generalization of graph convolutional networks, the overall property can and should be studied.
Thank you.
I have a question, Demba. I'm trying to figure out my video, but I'll just ask. This is Rich. Can I ask?
Yeah, go for it, Rich.
Okay,
great.
Rich, yeah. So actually, I was going to ask about this very slide. So it's very handy that the DSP framework is up. So are there any are there any extensions to any of this setting that you think might be interesting to look at, like going beyond like the setting, the setup that you have for the analog and digital domain? Is there anything you would think that might be useful beyond like the Borel space for the analog domain that your overall framework would handle, or are you limited to the mathematical tools that you get by using Borel space ideas? Does that make sense?
Yeah. So I mean, yeah. Thank you very much. Actually, first for this interesting question. So I mean, another setting these results hold true is if you have the analog domain is a very fine graph, or it is just a graph. So in these settings, I mean, these results also hold if you have a very fine graph in the analog domain. I mean, then your graph, your digital domain would be a discretization of that, a coarsening of that, and so then this also holds true. If you're asking about, let's say, even more general than a Borel space, I mean, then I might be hesitant to.
Okay, yeah, really interesting.
Yeah. Thank you.
Yeah, thank you.
And I have a question, Gitta Demba here, and this has to do with the DSP aspect of this. So is the band limited assumption, does that basically allow you to get smoothness on the underlying continuous space that is being sampled, which basically would enables you to interpolate using different coarsenings of the graph? Is that the intuition? In a certain sense, yeah. I mean, so certainly, I mean, the underlying, you mean the overlying analog domain. Yeah, so in a sense, you use, let's say, properties you would normally obtain from these Pauli-Wiener spaces. Like, yeah, so you say smoothness, but I mean, then, I mean, if you go down on the graph, I mean, you lose these properties. But yeah, in a sense, I mean, properties like what you say are used to a certain extent. Or if I can, yeah, go ahead.
Yeah, please, no, please.
Now, I was going to restate this. In other words, is it the fact that you have band limited functions that makes it such that after you sample a graph at one scale is somehow related to a graph at another scale, basically?
Yeah, I mean, yeah. So this is used, but I mean, it's not in a sense used that you let's say now use it to compare these two different graphs in a sense, because there, I mean, you don't have a scaling of the graphs. Now, so and in the end, I mean, we have two different graphs which we want to compare. I mean, there we don't have any notion of scaling or something like this. Now, so this is not used, but yeah. So in that sense, I mean, yeah, no, I mean. So the scaling property in that sense, I think, which you imagine, this does not apply here.
Okay, thank you. Do we have any more questions from the audience? There's a question from Akshay, who asks, one point of clarification, are graph CNNs rational operators?
So in which sense? I mean, so graph.
Can you please
CNN
clarify your question, Akshay?
Sorry?
I'm asking the asker to clarify the question, or you can unmute yourself and ask the question, Akshay.
Yeah, can you hear me now?
Yes.
Yes.
Yeah. So you mentioned that for transferability of Laplacians, instead of interpreting them as functions on the eigen functions, you would implement them as rational operators on the Laplacian itself. So I was just wondering if the graph convolutional networks are, I think you mentioned that the computations are more feasible if the operators are rational operators. So I was just curious about that.
Yeah, so this refers to the single filters in a sense.
Okay.
And the property and the let's say the way one sets this up is that these are rational functions.
Okay.
Yeah, so this is one filter which you apply. It's
okay.
not, let's say, the overall graph convolutional network.
Okay. And if I can ask one more question, I think there's a so would your results also imply transferability in certain cases to vertex domain filters as well? I think there might be some correspondence between spectral domain filters and filtering and vertex domain filtering, right?
Ah, okay. Yeah, I mean, I haven't thought about that. That's actually a very interesting question. I mean, it seems reasonable, but I mean, I would need to think about that.
Okay, thank you.
All right, thank you everyone for your attention, and let's thank our speaker again just for a very interesting and challenging talk. Thank you, Gitta. Thank you.
Thank you.